Thanks for viewing our presentation on evolving torque strategies for the 2020 Assembly Show. Here's the headline. It's all about torque and angle strategies. We're going to be talking about the evolution from torque to torque and angle, and more importantly, we'll be talking about what's driving this change and why it's so important. Stick with me till the end because everything in this presentation builds on the previous concepts. Now, you might not be familiar with the name Sturtevant Richmont, but chances are you're using our inventions. In 1924, Walter P. Chrysler has aluminum block racing engines that are blowing up. Steel had been around since the 13th century, but at the time, aluminum had only been around for about 100 years. So back then, aluminum blocks were considered to be very exotic and they were extraordinarily expensive. And you don't win races if your engines are blowing up. Even though aluminum's 100% recyclable, you don't want to be recycling a lot of engine blocks. Well, Chrysler's watching the workers build his engine, and he sees he's got two workers side by side that are bolting on the heads. One's 5'7" and 140 pounds, and the other is 6'2" and 250. Maybe this will help you picture it. The big guy's arms are bigger than the other guy's legs. And what Chrysler realized was that these two workers had very different definitions in answering the question, how tight is tight? Now, that's still the same question that engineers face today. Torque strategies have been evolving from that point, and it's the same question, but the answer has changed a lot. So Chrysler knew that he needed a referee. He needed something that would give the answer to how tight is tight. He also knew that steel had elastic deformation, meaning that when a sufficient load is applied to steel, it changes shape, and that change in shape is proportional to the load that's being applied. And when the load was removed, steel returns to the original shape. Chrysler applied Hooke's law and he invents the flat beam torque wrench. Now, Chrysler wanted to build cars, not tools. So he licenses Paul Sturtevant to manufacture and sell the flat beam torque wrench. Meanwhile, over at Lockheed Martin, there's a young engineer by the name of Frank Livermont. He's a bit of an entrepreneur. He leaves Lockheed Martin and he starts Richmont. So between the two companies, they invented the preset click wrench, the torque screwdriver, torque testers, micrometer adjustable torque wrenches, interchangeable heads for torque wrenches. These two companies drove most of the innovation in the torque tool industry. When Livermont invented the limited slip clutch for his torque screwdriver, Cleco sees it, they immediately wanted to buy the patent. They understood the value of what this invention carried. Livermont refused. So Cleco made him an offer he couldn't refuse. They bought Richmont. And much of Cleco's success has been built on the back of Livermont's patent for that limited slip clutch. Now later, Dresser bought both Sturtevant and Cleco, and in the process they got Richmont. Dresser merges the two together. Jack Reinertsen, who's a group VP of 6 companies that he acquired, is now charged with selling them off. He sells off 5 of the 6 companies. Hard to be a group VP when there's only one company left in your group. He realizes he's about to need a job, so he bought Sturtevant Richmont, and the Reinertsen family ran Sturtevant Richmont until 2017 when Snap-on acquired us. So for more than 90 years, we've been manufacturing industrial-level torque tools and testers. Torque's the only thing we do. We don't make sockets or hammers or pliers. There are plenty of companies that do that very well. What we bring to the industries that we serve is increased productivity through improved product quality, and we do that with error-proofing. So today's talk is about evolving torque strategies for Factory 4.0. Now, Factory 4.0 has shown a lot of promise, but when we survey companies across the industries that we serve, we see a lot of companies have yet to start on the Factory 4.0 path. Then on the other side of the spectrum, you've got like the auto industry, who's done a lot with Factory 4.0. In fact, the auto industry was doing 4.0 before there was a 4.0. Factory 4.0 is about connecting everything to the network. Connectivity gives you data and it gives you control because you can make processes contingent on other factors. So to control those processes in that network, you need an MES. Think about the computer network as the backbone of the industry. Well, the MES is the brain. The MES drives parameters down to the controllers on the shop floor. The controllers drive the tools. The controllers inform the operator which tool to use, how many fasteners are in the batch, etc. If there's a work instruction, the work instruction shows the sequence in which the fasteners must be tightened. When a fastener is tightened, the controller signals the MES, data goes to the data repository. And when the batch is complete, the MES sends down the next parameter and keeps that operator working. The data from connected systems can give you a lot of information that you would not otherwise have access to. And it's more about just information, it's about the right information. The right information has different definitions for different applications. That concept of control goes back to what we did for the car companies more than 20 years ago. It's a torque strategy that is still in use today, and it's evolved very little because the need has not changed. 20 years ago, we put a switch inside a preset click wrench. We used a cable to connect that wrench to a controller. The controller talked to the PLC. That system, as elementary as it was, did three simple but important things. It determined okay, no okay, it counted the batch, and when the batch was complete, the car could move to the next station. It didn't take long for safety engineers to take issue with the cable, and rightfully so. So within a year, we had embedded a radio in that same wrench, and that started our journey into the wireless error-proofing world, and we've never looked back. Car companies today still use that elementary system because it's fast and it does what they need. But needs change, and especially as assemblies become more complex, the need for change becomes more complex as well. If you think about that original system, it was modeled after DC tools. One controller, one tool, one operator. Today, we have controllers that work with multiple operators using multiple tools all simultaneously. And because of the digital torque and angle capabilities of our tools, this is really where we come full face with Factory 4.0. It's very much about data capture, data storage, data mining, and data distribution. And this is what makes product innovation possible. Our wireless systems have torque and angle capabilities from 5-inch ounces up to 600 foot-pounds. And it's the torque and angle data that gives better insight into what Walter Chrysler had considered when he invented the flat beam torque wrench. Chrysler was about the deformation of steel in the wrench. Today's engineers are using torque and angle strategies, but they're focused on the deformation of the metal in the fasteners. With torque and angle, you get a much more accurate assessment of clamping force than you do with torque alone. Torque by itself is a very cost-effective way of estimating clamping force, but 30% or more of torque is used in overcoming friction. So let's talk about process control and torque. There's a scope of process control and error-proofing. One end of the spectrum is a poka-yoke approach, which is a one-off error-proofing solution in a particular assembly cell, and it doesn't expand outside of that. It solves one problem in one cell, end of story. The other end of the spectrum is enterprise-wide implementation. We have solutions for both types of customers. Both types of customers are using torque and angle strategies, and they're doing it like never before. We've worked with poka-yoke error-proofing solutions, and we've worked with global implementation of torque and angle strategies. The global implementation process is never ending, and we've been working with some of our customers on global implementation for Factory 4.0 for more than 10 years, and they aren't complete yet. Here's where you have the confluence of two changes that really overlap. The market demand for changes in our customer's product has driven changes in their assembly processes, and those assembly changes are driving the changes in the products that we develop for our customers. Think about mixed model manufacturing. One product on the line requires these options. The next product right behind it requires completely different options. As these companies add options, the old ones don't go away. They just keep adding new ones. And that's what makes assembly more complex. We're seeing companies that once said a click wrench with okay, no okay was adequate. After all, a click wrench is simple, it's fast. But as assembly demands and parameters changed, the need for tools to evolve also grew. Here's why this is so important and why companies are using this torque strategy. If you can attain a more accurate assessment of clamping force, you can reduce fastener size. That cuts weight. Smaller fasteners also save money. And you think about all of the industries where weight matters, and you think about the number of fasteners that are used across a year, the implications are huge. Torque and angle also improves product quality and increases throughput. Why is that? You aren't spending as much time on rework and warranty costs. And that's the kind of thing that puts a smile on the CFO's face. Improved and more consistent product quality plays well with customers and your reputation in the marketplace. The new superhero today is actionable data. You've got to capture the right data. You've got to be able to store it. You need the ability to mine that data for business insights. You need a data repository or a PIM server. A PIM server is a product information management system. It can be cloud-based or it can be local. Capturing all the torque-related data on a fastener level is a daunting challenge. Remember what we said, that torque and angle is significantly more accurate than torque because 30% of torque is used to overcome friction? Well, this is how that plays into torque and angle. Now, instead of using torque alone, you're looking at thread count, you're looking at the pitch of the threads, you're looking at the material that the bolt is made out of, you're looking at the torque and angle measurements that allow you to take the bolt into elasticity and not stretch it to the point of damage. Here's one of the key takeaway points. Not only is torque and angle functionality important, but now engineers want the ability to graph a fastening. They're doing more than refining torque specifications. They're also assessing bolt quality. Now, maybe you've seen this in your plant. We're seeing a lot of bolts that claim to be grade 8, but they sure don't behave like a grade 8 bolt. They break much sooner and they stretch differently. So torque and angle is really a very much a quality process as well, or a quality strategy as well. You really start to understand the bolt. Without that torque and angle, you wouldn't see how they're stretching. The ability to graph a fastener with a torque wrench and assess that elasticity is really important. And our controllers have always been able to graph the rundown of a pneumatic tool, but now customers want the ability to graph a fastening using a torque wrench. And so that's something that is a seemingly small request, but it's seismic. But it goes back to, it's about data capture, data storage, data application, and it's about how many data points the customer wants for their graph to make sense for them. 5 or 6 years ago, we saw a lot of distributed databases. DC tools are an example of a distributed database. They tend to be standalone silos. If you're implementing an engineering change, you go down to the DC tool, you update the programming. Whether the programming change was the final torque value, the rotation speed, when it slowed down, you had to go to the DC tool and update that particular database. And you had to be sure that you did all the DC tools that needed that ECN. Well, the problem with that approach is that it's people-based or it's people-dependent. Someone has to physically go to that workstation and do the work. People get sick, they forget, they take days off. Things don't always go according to plan. So 5 years ago, the same customers that were emphatically against a centralized database are now migrating to centralized databases. And with everything on the network, now you don't have to go down to the workstation and update the programming. You can do it from anywhere. And this is where we add value to that data capture, data mining approach. Our controllers track engineering change notices for every fastener. We use the mid-2500 commands, and we know that at this date, this time, this operator in this station tightened this fastener, and it's tied to this ECN. Here's another application of data mining that customers find highly beneficial. You can't tell if a torque wrench is in or out of spec by looking at it. You have to put it on a tester. And if you find that a tool is significantly out of tolerance, you can use the data in that PIM server and go back and identify all the products that were made using the tool that is significantly out of tolerance. Using the tool that is significantly out of tolerance. Now you can go back, run a yard campaign, and find the fasteners that were tightened by the tool that was significantly out of tolerance. The real value to this is you can find the product defects before your customer does. You might be wondering, how effective can these processes be? One of the markets we serve is companies that have hydraulics in their build. Large or small hydraulic leaks are always a disaster. If you think about how things are built, a large portion of hydraulic lines are often on the inside of the product. And oftentimes they run multiple hydraulic lines together. That's a headache. You get a leak, now you have to try and trace the source of the leak. You might see hydraulic fluid on one line, but that doesn't mean that that's the line that's leaking. It just means that that's the line with fluid on it. So one of our customers found that it was often faster and more efficient to go back and rebuild the hydraulic connections to eliminate the leaks instead of trying to trace the source of the leak. The ideal solution is to prevent the leaks from happening. So how do you do that? Well, you have to ensure that all of the fasteners are tightened properly. There are a couple of factors that make hydraulics so challenging. You need a torque and angle strategy, and you need an operator to use two tools simultaneously. One tool would be a torque and angle wrench. The other tool would be a holding tool. So what's a holding tool? Well, 4 years ago, we invented and patented the holding tool as part of our torque strategy for hydraulics customers. If you think about hydraulic connections, torque application is really important. Too loose and it might not leak right away, but once it's out in the field, the vibration is intense. That fastener is going to come loose and it's going to leak. The other side of the coin gets the same result. If that fastener is too tight, the threads don't align properly and you get leaks. With hydraulic connections, tightening one fastener can change the torque on another part of that connection. When that happens, you get leaks. And of course, then add hydraulic hoses and even hard tubing to the equation. If a hydraulic hose is twisted by only 5 degrees, you lose about 70% of the useful life of that hose. Twist that hose by 7 degrees, and you lose almost 90% of the hose useful life. So we invented the holding tool to prevent this situation. And basically, we took our preset click wrench and we repurposed it again. Rather than applying torque, we use it to hold the fastener in place. And we put a radio in it so you know that the holding tool is engaged. The operator has to engage the holding tool first, then perform the torque application. And the holding tool must be engaged during the entire torque application process. And only after the fastener is judged compliant and the wrench clears can the operator remove the holding tool. The torque wrench used for torque application should be a digital torque and angle wrench. So how effective is this system of using two wrenches? The customer who had a significant leak problem, meaning that 72% of the builds had either immediate or latent leaks, dramatically changed. They went 30 months of build without a hydraulic leak. And when they had their first hydraulic leak after 30 months of perfection, torque application was not at the root cause of the leak. Torque and angle pays for itself very quickly. That's one of the reasons why it's an evolving strategy, because it's very cost effective and it makes a ton of sense. Here's another place where torque and angle strategy makes a real difference, and it shows how accurate and sensitive our tools have become. There are different modes of torque and angle calculations, and one of them is torque and angle monitoring. One huge advantage of torque and angle monitoring is that it identifies changing joint condition. We were doing a tool demonstration for the tack wrench, which is our digital torque and angle click wrench. We released this tool about a year ago. What we've done is we've taken a preset click wrench and we built in a digital brain. The tool operates like a click wrench because it is a click wrench, but it reports final torque and angle values like a digital wrench because it is a digital wrench. And it operates in torque and angle monitoring. And what's unique about this wrench is that it shows the operator two values. It shows where the wrench clicked and it shows where the operator stopped pulling. A lot of guys work with a mindset that they want to give it a little extra tug after the fastener is good and tight. They want to make sure that it's tight. By showing the operator both the point at which the wrench clicked and the point at which the operator stopped pulling, you get more consistent torque application. And torque and angle monitoring immediately identifies cross-threaded fastener, and it also identifies a double hit. A double hit is where the operator tries to tighten a previously tightened fastener. That alone improves quality and it improves throughput. Torque and angle monitoring also identifies changing joint condition. While we were doing a demo with the new tack wrench, we tightened one build with the gasket in place. And then we did the next build without the gasket. And the tack wrench immediately identified the change in joint condition. And that was created because the gasket was missing. The VP who's watching the demo said, "It's like this tool has ESP." Well, better than ESP, the tool is capturing actionable data and then applying it. The tool and the controller work together. They inform the operator about the fastening status of each fastener. Remember that if the operator ignores the click and continues to pull, and if they pull past the maximum torque value, they get a reject. We've been talking about hardening processes and actionable data. Here's where those two factors come together and you get immediate application of actionable data. If you're working on critical joints, our controller has a built-in feature that sets reject limits in a piece set. Your choices are 0, 1, or 2. If the reject limit is set to 0, every time you get a reject, the controller will freeze. And when the controller freezes, then the supervisor has to come over and release the system. If you set the reject limit to 1, the operator can have one reject in the batch and the operator can continue working. But if they get a second reject, the system freezes and the supervisor has to come and release the system. If you want to improve quality, the product will really be consistent. It's got to be consistent. And to produce a consistent product, the focus is on eliminating errors and doing it right the first time. After all, Harold Dodge says you can't inspect quality into a product, you have to build it in. And the last trend that I want to talk about is that we're seeing our customers embracing a greater commitment to product quality. And the way to that higher product quality is through torque and angle strategies. And now it's also through reject limits. So please come by our booth and talk with the team about your torque and angle strategies. We'd love to brainstorm with you. Thanks.